So, hello again. And continuing on the previous lecture, I just have to remind what was the content of lecture 1. And we learned several things. First, there are some astrophysical objects that are producing high energy particles going all the way up to 10 to the 20 electron volts. Second, in principle, we can try to figure out what's the population of the sources that dominate in the acceleration of cosmic rays. And this can be done through the indicators, which are actually the very, very broad band, clearly non-thermal emission. This is a clear indicator that something is going on in terms of particle acceleration. And then we considered common realizations of the Fermi mechanism. Basically, this is shock acceleration, and shock acceleration usually produces you a kind of a power law, though if you go into the details, you find that it's not just a power law, it's something more complicated than a simple power law, but in general, it's a power law limited by losses of particles, energy losses, or limited by particle escape. Oh, this produces quite a solid picture of particle acceleration, and you may think this is it. Basically, we can go into the details, but is there anything really not understand at the moment? And the answer is yes. If you go to relativistic shocks, the situation changes. Basically, the question is that we should ask ourselves, the question is, are the relativistic shocks the same, just very fast, or they are completely different beasts, and they should be treated differently? Seems that the particle acceleration mechanism that I described, the Fermi mechanism, is very robust, and it should work everywhere, no matter how fast is the shock. In fact, it's not like that. Of course, if we know that it's the famous saying that if anything can go wrong, then it goes wrong. Something goes wrong in relativistic shocks. First of all, think of the critical ingredient of particle acceleration that is done in continuing many cycles of the same nature. Particles should be reflected from the downstream, go to the upstream, gain energy, reflected from the downstream, etc., etc. How do we reflect a particle from the downstream if the shock is relativistic? I told you that any relativistic shock is strong, and since it's strong and it's relativistic, we know the solution. The downstream velocity is 1/3 of the speed of light. And then we can estimate what's the optical depth for particle scattering in the layer that actually reflects the particles. And the optical depth is given by this expression. If you plug 1/3 into that expression, you get 2. 2 is not really a diffusion. If you just have 2 mean-free paths, it's not really a diffusion. That's for the first. And here you can see it's just a kind of toy model. You try to scatter particles in random directions in the downstream of a relativistic shock. And if a particle, this is the solid line, if a particle doesn't have a chance to go back in just a couple of scatterings, then it's get advected from the shock and never gets back. This is a problem. This becomes even more serious if the magnetic field is regular. Then every relativistic shock, because of Lorentz transformation, the magnetic field lines become aligned with the shock plane. And a particle, if the magnetic field is uniform, a particle starts to gyrate across the magnetic field lines. The gyration center moves with the speed of 1/3 of the speed of light, moves with the speed of the downstream. The particle itself moves with the speed of light, and to complete a gyration, it needs pi times r. During this time, it goes away with the average velocity of 1/3 of the speed of light by a larger distance than r. So a particle in a uniform magnetic field never comes back. They never can be reflected from the downstream, and you never get acceleration in a relativistic shock in a uniform magnetic field or ordered magnetic field. So you need disordered magnetic field. For the disordered magnetic field, you can, in principle, think of kind of Fermi-type acceleration. For that, of course, you have to assume that, yes, you can, in some way, to approximate the situation as a solution of diffusion equation. This has been done by some people. They got some answer, which is written here. The spectrum, of course, is, again, a power law, but the spectral index is 2.2, approximately. Well, it's fine. It would explain many things where we really observe acceleration, efficient acceleration in relativistic shocks. But, as I told you, this is kind of diffusion approximation. In this case, it was actually not just the diffusion approximation, it was diffusion over pitch angle. So every scattering is by a small angle. This approximation is, it was done not because we knew that this is the case. It was done because this is the only way we can solve the problem analytically. So it's not really, I would say you shouldn't believe that. You shouldn't believe that in the sense that you need some proof that the scattering properties are indeed similar to what was assumed. And this was a long-standing challenge for the people to model this numerically. And the first report was less than 20 years ago. That yes, they started to see kind of emerging power law tail from the thermal distribution of particles. But there is a subtlety in numerical simulations. They are 2D, and in 2D, a relativistic shock has downstream velocity of 1/2 of the speed of light. So it's not exactly the same situation. Anyway, much time has passed, and actually from the same people, partially from the same people, we get a much longer simulation where they investigated how this distribution evolves, and you see that up to the end of their simulation, it's still continuing to evolve, and we don't know what's going to happen in the end. Moreover, you see how this tail is evolving. This tail is going to higher energy, the cutoff is going to the higher energy, but also the tail itself goes up. In energy, in principle, we have no limit, in principle. But in the height, we have a limit. We cannot have more energy in the tail that we have altogether in all the particles. And that means you cannot be sure that you don't stop somewhere. Just being limited by the total energy content in the particles. So the question remains, though people tend to believe the simulations in a sense that they kind of prove that, yes, there is Fermi acceleration in a relativistic shock as well. But for that, of course, you need a completely disordered magnetic field, which is actually generated by the particles at the shock itself. So the plasma before the shock should be unmagnetized, as they say. So magnetization is produced by the shock, and it produces another problem in this kind of simulations. The magnetic field, which we see in the simulations, is very short-lived. If you want to produce synchrotron emission, and we know that relativistic shocks do shine in the synchrotron, then you are in the trouble because the magnetic field doesn't survive long enough to produce significant synchrotron emission. Something is definitely incomplete in this picture. Now let's try to go deep into the field by choosing some object. And I told you in the previous lecture that relativistic shock that is produced by gamma ray bursts, during their afterglow, we see this emission of this external relativistic shock. This is the cleanest problem we can imagine in astrophysics. It's just a shock as such. So it's a relativistic shock propagating into unmagnetized medium with some density, and this is a very well postulated problem that, again, I told you that simply postulated problem doesn't mean that it has simple solution. Solution is not at all simple. Okay, now let's try to do the same exercise that we have done at the previous lecture. Let's try to think, we know how the position of the cutoff in the synchrotron spectrum, which is induced by losses of the accelerated electrons, radiative losses, we know how this position is related to the velocity of the shock. But in this case, we know in advance that the shock is relativistic. Let's try to see if it's consistent or not. The synchrotron burn-off limit, this is the maximum energy that you would observe in a relativistic shock. It's also blue shifted because the shock itself has a very large Lorentz factor of 100 and something, maybe 200, 300, something like this. So it's close to 10 GeV, more or less. You see where is the synchrotron peak? It ends somewhere here. If we believe that this cutoff is due to the synchrotron emission of the electrons, this implies that the acceleration efficiency is again 10 to the minus 5, and this is unbelievable for a relativistic shock. It should be something like one-ish, as they say. What can we do? Remember another picture from the previous talk? Actually, we have a thermal population of the particles that are thermalized at the shock. And then only from that, you extend power law tail. So maybe this peak in the synchrotron is related not to the tail of particles, but to these thermal particles, which are just being produced thermally at the shock. Well, first of all, the thermal particles, they have really narrow distribution in energy, and the synchrotron peak is really wide. This is already kind of a trouble, but then you can try to invent something. The more serious problem is that this kind of assignment implies definitely that the energy of particles here, the average energy of particles here, and in the thermal distribution, is just proportional to the Lorentz factor of the shock. The proportionality coefficient is something that you can choose, saying that, okay, we don't know the details of the theory, so it can be 0.1, maybe 0.01, maybe something like close to 1, but it is proportional to the velocity, to the Lorentz factor of the shock. When the shock decelerates, this energy should go down. This is a very firm prediction of this assignment, and you cannot get rid of it. Before we try to understand what's going to be, what's going to happen in reality, let me discuss some physics which is involved into this kind of radiation. First of all, we have synchrotron radiation. This, I believe, is known to everyone in the auditory, but just to give you some reminder, the energy of synchrotron photons is proportional to the square of their Lorentz factor. The power, the emitted power of the electrons is proportional to the square of the Lorentz factor of electrons, to the energy density of the magnetic field, and here is the cross-section, Thomson cross-section. And yes, there is, for the synchrotron, there is a kind of upper limit for the energy of synchrotron photon that you cannot violate. Beyond that, if you have an emission beyond that, it's not synchrotron, almost certainly. Then we have inverse Compton. Usually, in this situation, we describe this as SSC synchrotron self-Compton. That means the soft photons, which are upscattered by high energy electrons, these are the synchrotron photons of the same population of the electrons. So electrons are producing synchrotron photons. They are relatively low energy photons, and the same electrons are then upscattered these photons. If you have scattering, this is called inverse Compton because you remember that Compton has discovered that if you have a high energy photon hitting an electron at rest, then some energy is transferred to the electrons and the reflected photon has less energy. Now the situation is completely different. The energy of a photon is much less than the energy of an electron, but the same scattering occurs and the energy is transferred the other way around. This is inverse Compton. So you take some energy from an electron and give it to the photon. And if we write down the power of this inverse Compton emission, then it's again gamma squared. It's again the energy density of the electromagnetic field, now the energy density of the low frequency photons, times the cross section of scattering, for scattering between photons and electrons. At low energies, this cross section is Thomson cross sections, but at high energy, it becomes lower, it becomes Kleinisch inner cross section, it goes down. What does it mean? It means that in Thomson regime, you have very high efficiency of producing inverse Compton radiation, but the energy of the inverse Compton photons is not that high. It can be, in principle, much lower than the energy of an electron. In the Kleinisch inner regime, it's the opposite. Essentially, you transfer almost all the energy of an electron to the upscattered photon, but the efficiency, the cross-section, becomes low. If you want to have both at the same time, you want to have high efficiency and high energy of the upscattered photon, you have to be between the two regimes, so just at the verge of the Kleinisch. Why we can say this in advance? Because if you go back and see the spectrum, the energy here is high, and the efficiency apparently is also high. You have approximately the same luminosity in inverse Compton as in the synchrotron. So this gives you a hint. It's not a proof, but this gives you a hint that you must be somewhere in between. And finally, if you have inverse Compton, you turn the Feynman diagram for the Compton scattering by 90 degrees, and you get 2 photon per production. It's just the same process. If you don't ignore the inverse Compton, you say it's an efficient process, you cannot ignore pre-production. It's just the same process with the same cross-section, different by a factor of 2. So it has to be included. This is something that some people tend to ignore in their simulations, but it cannot be done in a good way. I mean, if you ignore this process, then you probably miss something really important in the physics. So these are the 3 important processes. The others can really be ignored. At least we believe that this is okay. Now, what are the parameters that regulate solutions for the SSC? Once again, SSC is that you have a population of electrons. Essentially, you assume that the electrons are being injected into the system at some rate and with some distribution over their Lorentz factors. This is the distribution, and the distribution is motivated clearly by the fact that whenever you have an acceleration, you produce a power law. So it's a distribution that has a peak cut at low energies to get the distribution integrable, and at high energies you have just e to the minus p distribution, which is a power law. P is some number that usually people take something like 2.2 or 2.5, something like this. So this is what you assume actually. Then you have the 4 real parameters: the magnetic field strength, the Compton potential, or the ratio of energy density in the electrons to the energy density in the magnetic field, the scale of the injection function, the typical energy of injected electrons, and finally you have the so-called Coulomb-Lorentz factor. That means every physical system has its typical dynamical time scale. Over this time scale, with a given magnetic field, if you inject an electron with an infinite energy, it will just cool down to some gamma c. This is called the Coulomb-Lorentz factor. Or equivalently, given the magnetic field, you can just tell the time, the effective time scale. Or equivalently, if we have a relativistic shock, we know the observational time, we know the Lorentz transformation, we can just calculate this T efficient through the observational time and the Lorentz factor of the shock. This is all equivalent, but in principle, it's just the time scale. The 4 parameters. Then, if you have diffusive shock acceleration, then regarding the the injection function, I told you that there is no way you can avoid this proportionality, that the injection Lorentz factor is proportional to the Shocks Lorentz factor. It's just the proportionality that you cannot avoid. You can play with the coefficients. And people do that. Actually, most of the coefficients are taken from the particle and cell simulations. But since the field actually started to develop before the real trustable particle and cell simulations were started to appear, some numbers just traditionally are a little bit different from what you see in the particle and cell simulations. It's just a tradition, but it's not really that important. Though you may think that this is an order of magnitude, it's a huge difference. No, in astrophysics, it's not a huge difference. It's just almost the same. Okay, so what's the real situation if you do not ignore production of electrons and positrons by gammas? Remember, I told you about, in the previous lecture, I told you about the pressure that accelerated particles introduce on the incoming flow. Now it's even clearer. You have photons escaping from the downstream to the observer, and these photons are high energy photons, inverse Compton, and low energy photons, synchronous photons, and they can interact producing pairs. They can produce pairs in the downstream, this is fine, and this doesn't introduce any trouble, but they can also produce pairs in the upstream. If they produce a pair, this pair starts to interact, it entangles with the magnetic field in the upstream, and it loses its directional momentum. It doesn't lose its energy, but it loses its momentum. So it's a momentum transfer. It's a force imposed on the incoming flow, and this incoming flow starts to decelerate. If you produce too many pairs, that means the incoming flow decelerates almost completely, and you don't have a good relativistic shock. Just the flow gradually decelerates and goes into the downstream. So imagine that you started from some population of electrons in the downstream. Suppose they are low energy electrons. That means they produce low energy synchronous photons and low energy inverse Compton photons. And then you don't produce many pairs because there is an energy threshold to produce a pair. The product of two energies should be more than mc squared to the second power. It's a kinematic threshold, and if you are below that threshold, you do not produce many pairs. You still produce something because of the tails in the distribution, but they're just a few. And all the energy of the incoming flow goes to the acceleration of these very few pairs. They really attain a very large energy, and then when they go to the downstream, they are very energetic particles. They produce very energetic synchronous photons and very energetic inverse Compton photons. What happens then? You produce pairs very efficiently in the upstream, and very efficiently means you produce very many pairs, but the power of the incoming upstream is limited. So if you have very many particles with the same power, you just distribute energy over these particles, and every particle attains lower energies. And this is a self-regulating mechanism which settles somewhere close to the point where you just start to produce pairs efficiently. That means that the product of the Lorentz factor of an electron times the energy of a photon in the common frame is just equals to mc squared, and that sets you a relation between the typical Lorentz factor of electrons and the magnetic field. Now it's not a relation of the Lorentz factor of electrons with the Lorentz factor of the shock. It's the relation between the Lorentz factor of electrons and the magnetic field strength. It's completely different, very different behavior. Moreover, it's not just different, it's different qualitatively, because as the shock expands, the energy density behind the shock in the downstream goes down, and that means that in general the magnetic field goes down. And if the magnetic field goes down, then the Lorentz factor of electrons goes up. So it's just the opposite. We should be able to see the difference. These are very different predictions. And, well, just maybe a little bit more into the details. This doesn't influence too much the rest of my talk, but just for you to understand how the physics, the real physics works here. What you can do? Once again, you write energy, momentum, conservation equations, but now you have some outflow of the energy in form of photons, which are then produced in pairs. So some energy is going, the energy not just going from the upstream to the downstream, some energy is going from the downstream to the upstream. And to take this into account, you introduce some terms which account for the energy flux in the opposite direction. Then equations become kind of not really easily solvable, but you can do something with that. What you can do solving these equations are the following. So that in general, the solution would be like that. You have in the shock frame, you have the incoming flow where the Lorentz factor at infinity is very large. Let's say it's infinite. Then the flow slows down, but it slows down not entirely. It produces the so-called viscous subshock, where the flow is being actually decelerated from the supersonic to the subsonic. This is what creates a shock. A shock is a transition from supersonic to subsonic flow. And this jump is not necessarily equal to the initial difference of the downstream and the upstream Lorentz factor. What you can do, solving the equations that I have shown you, what you can do is you can try to solve for the structure of this precursor of the shock, and you can try to solve for the jump, for the viscous subshock. And regarding this jump, you get a solution. Here you see the curve. The upper branch is for this velocity, and the lower branch is for this velocity, the actual downstream velocity. So the upper branch is the velocity of the flow just before the subshock, and the lower branch is for the velocity of the shock in the downstream. What you see is that if there is no absorption in the upstream, you just reproduce the normal result of the taube, that in the downstream, the velocity of the flow is 1/3 of the speed of light. And if you start to increase this absorption parameter, the velocity of the downstream rises, the velocity of the upstream at the subshock, once again, it goes down. Essentially, they meet somewhere at the point where these velocities are both equal to the velocity of the sound in the relativistic fluid, c over square root of 3. And then at this point, you really lose a shock at all. This is just a smooth transition from the relativistic, from the supersonic to the subsonic solution without a shock. If you want to have a shock, and you really want to have a shock, to at least to start the acceleration of particles, then you should limit your absorption parameter by something like 0.1. Then you still have a subshock, which is kind of mildly relativistic, the subshock itself. So the predictions of the pair balance models. First of all, if we do this pair balance, that means that you need to have enough inverse Compton radiation to balance the shock. Enough means that the inverse Compton radiation is not really much smaller than the synchronous radiation. On the other hand, if you produce too much inverse Compton radiation, then the shock is kind of overbalanced. So the general prediction is that the ratio of inverse Compton to the synchronous luminosity should be about 1. The second prediction is that I just explained to you that the Lorentz factor of the particles is regulated by the magnetic field in the shock and not by the Lorentz factor of the shock. And then the fraction of internally absorbed radiation is either constant at 0.1, or if the shock cannot maintain the absorption that high, when it slows down, you definitely, at some point, you cannot do that. then the shock at least tries to be the most efficient in terms of the absorption, and that means the Lorentz factor is given by this expression, inversely proportional to the cubic root of the magnetic field. And all the energy goes to the accelerated electrons because they are the ones that balance the shock. So the fraction of accelerated electrons is just 1. Nothing goes to the protons. Well, when I'm saying nothing, that means we consider a simplistic problem. Of course, something goes to the protons, but it's not a significant fraction. Okay, then these are two sets of predictions from the diffusive shock acceleration and from the pair balance. They are very different. Let's try to check which one really holds. This is the first gamma ray burst which was observed in TV, and TV is essential because you remember the SSC parameter space has 4 parameters. 4 parameters means that you have to solve 4 equations. You have to basically to introduce 4 observables to solve these equations to get 4 parameters in the to get to the point in the parameter space. What are these 4 observables? The position in terms of frequency of the synchron peak, the height of the synchron peak, the position in terms of photon energy of the inverse Compton peak, and the height of the inverse Compton peak. These are the 4 observed parameters which can be kind of recalculated into the 4 parameters in the parameter space. If we do not observe the inverse Compton peak, we have just 2 parameters, the position and the height of the synchron peak, and this makes the problem degenerate. You can always fit the spectrum to some extent with very, very different assumptions. This doesn't give you a clear solution of what's going on. But once we have the inverse Compton peak, the TV measurements, we can do that. And fortunately for this burst, we have observations at different times, so we can have also an idea of what's the evolution of the parameters. So the first fit for the early time, 90-second, is giving us these parameters. You don't have to remember these parameters, but you can see how good is this fit. This was actually surprising because the fit is done in the so-called one-zone model, where all the particles have the same distribution everywhere. It's a uniform zone with a uniform magnetic field, a uniform particle distribution, and you see how it reproduces the spectrum. This was kind of surprising because it's really a spherical cow. By the way, is younger generation is familiar with this meme, spherical cow or not?
Spherical horse usually.
Yes, sometimes in Russian tradition, sometimes it becomes a spherical horse. No? You don't? Okay, then after lecture I will tell you. Okay, so it's a very simplistic approximation, but it still produces very good results. Surprisingly, but okay, why not? Then at later time, again, you can produce very good fits. These are two slightly different curves, which are both good fits. Actually, they are different between them. And this difference is because of some assumptions about the evolution of the Lorentz factor of the shock. You may go into these assumptions, you may not. Anyway, you produce a good solution and you produce the fit. So let's compare. Without going into the details about that, about how evolves the parameters characterizing the magnetic field itself and characterizing the fraction of the energy in electrons, let's look at the first line. Gamma B, this is the Lorentz factor that characterizes the energy scale of the injection, is 6,000 at the early time, and then it goes up to 16,000 at late time. This is what we expect in the pair balance model, and this is what we do not expect in a normal diffusive shock acceleration. Moreover, you can calculate the fraction of internally absorbed radiation. Since it's a model, you can do whatever you like. You can calculate this fraction as well from your calculated spectrum. And it's 10%. Not only it's 10%, it's 10% staying constant. It's 10% here and 10% here. But if you just do the normal assumptions, then this fraction should evolve very quickly with time, something like as fifth power of time or something like this. And it does not. Then the next burst comes. And by the way, the situation is very funny. You know, there are two bursts actually from approximately the same time, and afterwards, after 2021, we see nothing. It's like for supernova in our galaxy. We should see them once every 30 years, but we don't see them for hundreds of years. I don't know what's going to happen. The gamma ray bursts are cheating us, perhaps. But anyway, we have the second example, and this second example is good in the sense that we have observations at really late time. One of the observations is 8 hours after the burst. Another one is on the second night. The Cherenkov telescope is something that is working only on the night time, so the second observation is delayed by 20-something hours. And these are the figures from the discovery paper, and you see they cannot fit. The blue line are the curves which they tried to produce under the standard assumptions. No way. So what they did desperately, they said, okay, maybe somehow there is no burn-off limit for the electrons, and they just accelerated up to the very high energies. And it's just a single power law extending from here to the TV energies. Oh, I said it's a really desperate solution. It's not motivated from physics, it's motivated from the fact that they could not fit with a simple model the spectrum that they observed. If you don't restrict yourself to any model, you just go over the whole parameter space, four-dimensional parameter space, just to see if there's any point in the parameter space that you can fit the spectrum, and yes, you find this point. But then the Lorentz factor of injected electrons, and remember this is a late time, the Lorentz factor of the shock itself should go down significantly up to maybe 10 or something like this, but the Lorentz factor of injected electrons should be 10 to the 5. Furthermore, you go to a later time, you calculate the Lorentz factor of injected electrons, and it's still 2 times larger. But you can also estimate the magnetic field. And if you just try to calculate from the magnetic field, you try to calculate which is gamma naught, that should be the typical scale for the Lorentz factor, you see. It's fantastic. So these are, by chance, these are just 2 examples. One is the saturated pair balance solution when you are limited by the maximum allowed fraction of the absorbed radiation. Another one is insaturated solution when you are not limited, but the shock itself balances it in a way that it produces the maximum possible absorption. By the way, in other words, if you formulate it in other words, if you go for this solution, then it means that the shock overall the shock's overall luminosity is the maximum. So the shock tries to be as luminous as possible. It tries to be as much radiative as possible. And here is just a general diagram when I tried to summarize different things that we can measure from, that we can judge from the measurements, from the observations. And let's check whether the conventional model and the pair balance model fit these facts or not. Well, the conventional model is SSC plus diffusive shock acceleration. The pair balance model is the same SSC plus the converter acceleration mechanism. I will just tell you a little bit more about that. Yes, basically it tells for itself. It's kind of going to become all red the left column, and the right column is all green. I think the distinction is clear. The only thing that prevents me from saying that the question is settled is that the statistics is not fantastic. We have only 2 examples. But both of them are fitting nicely the predictions of the pair balance. Okay, before we go to that, maybe I will shortly interrupt and ask you a question that I promised to ask you in the previous lecture. Once again, remember, we tried to estimate from the position of the cutoff in the sectoral spectrum, we tried to estimate the Lorentz factor, the velocity of the shock in the Crab pulsar. And we tried to do that in the diffusive shock approximation, and this diffusive shock acceleration approximation gave us a result that yes, the velocity of the shock in the Crab pulsar is close to speed of light, and this was a kind of nice agreement with what we expect and what we calculate from the diffusive shock acceleration. Now you should ask me the question. No, everything seems fine to you, right? Okay, the question that you should ask is the following. I just told you that diffusive shock acceleration does not work in relativistic shock. So how comes that in Crab pulsar we see a good agreement with predictions of diffusive shock acceleration? Well, I told you that the question itself is worth of money. So the answer is worth of millions of dollars. It's $1 million question. I don't know. Maybe in a Crab pulsar we still have converter acceleration, but in a very, very specific regime. Maybe. But this sounds really strange even to me, though I was proposing that. I don't know, really. I don't know. So it's a big question. This is one of the situations in physics. If you don't go deep into the problem, you think, oh, it's fine. It's just in a good agreement with all I know. If you try to go deeper, you find, oh, it's a really, really big problem. Though at first it seems to be in a good agreement with everything. So regarding the converter acceleration, what I was telling you was just one cycle of this converter acceleration. You cannot do more with electrons because they lose energy very quickly. The photons go to the upstream takes these pairs and gives energy to the pairs, energizing the electrons and positrons, and then they quickly lose this energy for synchrotron and the inverse Compton in the downstream. That's it. Then you can repeat the cycle. It's not diffusive shock acceleration. It's just the same cycle repeated many, many times. You don't really gain energy. So you gain energy inside the cycle, but not from cycle to the cycle. This makes a difference. But imagine that you have not only electrons, you have also other particles. For the electrons, what do you have actually? You have a charged particle in the downstream that gives energy to a neutral particle, to the photon, and then this energy is again given back to the charged particles in the upstream. In a sense, it looks like you switch on and off particles charge. Of course, it's not like that. Of course, it's just transition of energy. But in a very simplistic way, you think of a situation like you have a switch for the particles charge. If you don't want a particle to have a charge, and you don't want it, if you go from the downstream to the upstream, the magnetic field that acts on the charge is only an obstacle for you. You don't have any gain from the magnetic field. You would like to switch off the charge when you go from the downstream to the upstream, but you want to switch on the charge if you want to energize a particle in the upstream. So, of course, it's a stochastic process, and in some cases you will have it just the other way around, but these are not going into the acceleration process. So the unfavorable phases are going out, but favorable are just like that. But we have the same for protons. Think of a proton that is energetic enough that it interacts with the photon and it produces a charged pion and becomes a neutron. In this way, yes, you lose some energy for producing a pion, but most of the energy stays in the neutron. You switched off at the expense of some losses in energy. You switched off a proton's charge, and then you can switch it back by the same interaction of a neutron with a soft photon, producing another charged pion. Now it's pi minus, and getting back the positive charge. Or a neutron can just decay freely. If you have enough time, the neutron can just decay. Anyway, you have the same situation, and yes, you have a collisional channel when you have two protons producing, again, a charged pion and the neutron in the collision. Anyway, you have situations where you lose some energy, but at the expense of losing energy, you can switch the particle's charge on and off. If you have just a uniform environment, this is called a cascade. This is a way a particle is gradually losing its energy, producing more and more secondaries. Nothing like that. But if you have a non-uniform medium where the velocity in one place is significantly means there is a relativistic difference in velocities, is different from the velocity in the other space, in the other part of the space, then you can go back and forth between these parts. And if you switch on and off charge in the right phases, then you start to accelerate. And since there are, yes?
The question is that I can see that the proton, this one reaction happens more frequently than the second one because neutron doesn't really have charge.
You mean
yeah,
here?
1 and 2, not like the leptonic case where it's the same order of magnitude.
It's also the same order of magnitude. I will show the cross sections. Yes, this one and this one.
I mean, neutron scattering is the gamma ray. It has
Yeah, it's the same order of magnitude. Yes.
really.
Yeah.
Neutron has no charge. It only interacts with
Because it's an electromagnetic interaction with the constituent quarks. And
so the energy high enough, you get the.
yes. You excite the internal degrees of freedom of a nucleon, and since the content is, well, it's not the same, but it's similar. For a proton and a neutron, then you have similar cross sections. If you have to rely on that reaction on a free neutron decay, then yes, they are different and by definition, yes. So, as I told you, not repeating it too much, the cross sections for gamma electron interaction is roughly the same as the cross section for gamma-gamma interaction. This is clear. And again, here are the cross sections for the proton-neutron, for the proton-photon and neutron-photon interactions, and you see this big resonance. When you produce by an incident photon, you excite delta resonance, switching the spin of one of the quarks inside the nucleon. This essentially creates you a pair of quark-antiquark, which splits from a nucleon and produces a pion, and then you can redistribute quarks in a way that you lose the charge. And
But this process is effective at low energies, like GeVs.
no, it's not. It's not. You have to start it. It's like an old engine. You have to jumpstart the process. You have to. To accelerate particles up to some threshold energy, yes, you are absolutely right. You have to pass some threshold energy in one or another way. But after that, you can accelerate. In principle, if you have an extremely relativistic shock, like gamma ray bursts produce early in their life, then even thermalized, the particles thermalized at the shock may just get the right energy to start the process. But if you have a Lorentz factor of 10 or something, then you have to introduce something else that first pre-accelerates particles, and then you go from that to higher and higher energies. Unless you have a collisional way of doing that, but for that you need high densities, which are not the case at least for the external shocks and gamma ray bursts. What's the critical difference of this acceleration in the converter way from the standard thermal acceleration. I told you that the big trouble in the accelerating particles in the relativistic shocks is that you lose them to the downstream very easily. So the probability of particles staying in the acceleration process is relatively low. In principle, if you have a particle that goes from the downstream to the upstream, it goes with the speed of light. First, it goes faster than the shock itself. The shock goes at almost the speed of light, but a particle goes at almost exactly the speed of light. So a particle is overtaking the shock at first, and then it starts to be deflected by the magnetic field. When the deflection angle is about 1 over gamma, then the shock catches up with the particle, and that's it. The particle goes back to the downstream, and the energy gain in this process is something like factor of 2. Now it's a big question whether you can really balance this factor of 2 by probability of reflection from the downstream, which is also not very high. It can be really less than 1 over 2. But what you have in the converter acceleration is that you produce a particle which is now a neutral particle. It goes away as a neutral particle, and it's not being deflected by the magnetic field. So it has some time. When it becomes charged particle again, it has some time. The shock now is not right next to the particle. The shock is behind the particle. And in the time when the shock goes from position 2 to position 3, the particle has in principle a possibility to complete the entire cycle. It can isotropize its direction over the momentum, and the Lorentz factor and the energy boost would be just the Lorentz factor squared. And the Lorentz factor squared would easily compensate any losses in the downstream. So in principle, this acceleration produces you very hard spectra. Of course, it depends on the Lorentz factor squared. If the Lorentz factor squared is 1 point something, then it's nothing. If Lorentz factor squared, like in gamma reverse, is 10 to the 5, then it's way too much, maybe, even so. Okay, very quickly, the probability of conversion, just to see whether it can be compensated. In this cycle, it's not the probability of reflection that goes into the play, it's the probability of doing the conversion cycle, so the probability of interaction in the right way. The probability of conversion for electrons and, sorry, it's not for electrons, it's for active galactic nuclei and gamma ray bursts, and this is probability of conversion for the protons. And you see, it's not that small. In principle, it can be compensated by the Lorentz factor squared. But yes, I have to confess that this is kind of optimistic estimate. So in principle, it means that both in gamma ray bursts and in active galactic nuclei, you can do this converter acceleration. You can accelerate protons. What makes the converter acceleration very different from other ways of accelerating particles? You cannot accelerate nuclei in this way. You cannot switch off charge of a nucleus. No way. You can only break it apart into the nucleons. So there are two acceleration mechanisms which seems to be kind of working in relativistic shocks, but they almost complementing each other. They have weak points and they have strong points. The weak point of the converter acceleration mechanism is that you have to pass some energy threshold, as Dim just asked. You have to go past some energy threshold to start accelerating efficiently. This is the weak point, and well, it requires relativistic velocities, relativistic shear flows, jets, or relativistic shocks, whatever, but it should be relativistic to compensate for the energy losses. But in all the other aspects, it's a very efficient mechanism. It does not depend on many problems, on many things that create problems for the diffusion shock acceleration, like the geometry of the magnetic field lines, the things that make the situation fragile in the sense that you cannot really predict what's the geometry of the field lines. It's theoretically, it's a formidable task. You cannot do that. Numerically, you can try, but then the question is whether you really can believe the numerical simulations 100% or not. So this is my summary, but after the summary there will be a teaser for the new physics and almost traditional opinion poll for the auditory. The summary is like that, if you try to summarize all this. Relativistic shocks are really different from non-relativistic shocks. Where there is the border, it's difficult to say, but the border is probably close to gamma 1.5 or something like that. And you start to lose efficiency of diffusive shock acceleration before you really get into the region where the converter acceleration becomes efficient. So something should happen with the shock in between, where both acceleration mechanisms are inefficient. One is still inefficient, another is already inefficient if the shock accelerates. Maybe it is smeared out by the fact that you see different parts of the shock at slightly different time because of the arrival delay. And maybe this is smeared out and compensated. We don't see any signs of clear transition in the light curves of gamma ray bursts that something terrible happens to the light curve. Something happens, but this is to be explored, and this is really difficult physics when you cannot introduce simplifications like the Lorentz factor is infinite or the Lorentz factor is unity. Now the Lorentz factor is something which is not infinity and neither unity. It's a complicated problem. Anyway, if you consider gamma ray burst in the stage when the Lorentz factor of the shock is still high enough to be sure that the converter acceleration works, we see that at least for electrons, the converter acceleration provides a very good solution to what we see, very good fit to the observations. And that probably means that in gamma ray burst for electrons, the converter acceleration works. If it works for electrons, there is no reason to believe that it doesn't work for protons. Although we cannot see that because protons do not radiate. They will be emitted as very energetic particles from the gamma ray burst, but basically that's it. It's very difficult to distinguish an observable emission sign from the accelerated protons. So probably they are accelerated, but we cannot be exactly sure. And basically that's it for the converter acceleration, but it's not the end of my talk. Now it's really new physics, even unpublished physics. What we did, we tried to simulate a relativistic shock numerically with particle and cell setup, traditional setup, but what's not traditional in this simulation is that now it was quite a challenge. Now our computational frame is moving with the velocity of the shock. So the shock in the computational frame doesn't move. It's the standard frame that you use in theoretical calculations, but it's very non-standard in simulations. In simulations, you usually a standard frame is downstream common frame. So downstream is at rest in the simulation frame. And that way, we can follow the shock for much longer time with much less effort put on that in terms of the CPU hours. And our simulation was actually 4 times longer than the record simulation that I showed you from the previous year. And you see what happens. If you see, look at the particle distribution, yes, first it evolves, and the tail goes to higher and higher energies, but at some point it stops to evolve, and it goes to kind of steady state solution. Yes, you do have the second component, but it's not a power law at all. It's just a second component of the particle distribution at high energies, and that's it. Here you have an exponential cutoff still, at energy which is just 10 times, I believe it's 10 times higher than the thermal energy of the particles just thermalized at the shock. This is a headshot for the diffusive shock acceleration, even numerically. And the reason for that was kind of clear immediately. This is a map of the magnetic field strength in the downstream. By the way, you can try to guess where is the shock. Is it here, 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 or here? It's just some portion of the downstream. Where is the shock? Can you guess? Looks very isotropic, right? So the shock is here actually, and the flow is going from here to here. But you don't clearly see the evolution now because the evolution is already slow. Everything fast happened close to the shock, and this is far in the downstream. And you see what's the geometry of the magnetic field. Well, yes, it's 2D simulations. You can always say me that 2D is not 3D, and who knows what's going to happen in 3D. But we have good reasons to believe that in 3D it should be quite similar. You cannot say that the scattering of this magnetic inhomogeneities would be something like speech angle diffusion. Nothing of the kind. It's something completely different. If a particle strikes this magnetized region, then it gets reflected. If it's not, then it goes through. It's like that. Many particles escape into the downstream. This is the reason why you don't continue the acceleration indefinitely. They just escape. They have no chance to scatter of anything. They just go to the downstream and that's it. They are lost. And, sorry. Here's the quiz time. I promised you to have an opinion poll. Am I allowed to do that on a blackboard? So the situation is like that, just to make it clear. I want to address your physical intuition and you tell me what sounds more attractive to you intuitively. So you have a relativistic shock. You go into the frame of the relativistic shock because if you think of a laboratory shock, then all the distributions are beamed forward with a beaming angle of 1 over gamma. So you are working in the common frame, common with the shock. Now think of the distribution of accelerated particles, not thermalized particles at the shock, they are more or less isotropic, but of the accelerated particles, of these particles from this distribution. What you think is the distribution of these particles? And I could imagine, maybe you can imagine something else, but I could imagine 4 possibilities. One possibility which is split in 3, it's that the particle distribution is elongated along the shock propagation direction, along the shock normal, and then it can be more or less symmetric, forward and backward. It can be more shifted to forward direction, and can be more shifted to backward direction. Once again, I have to remind that this is in the shock common frame. The other way is then you, from the symmetry of the problem, you don't have a preferred direction. The particle distribution can be extended in the shock plane, so it's flattened along the shock propagation direction. What do you think is the right situation? And
are we still talking about 2D case here?
sorry?
Are we still talking about 2D case here?
2D.
Yes, two-dimensional case.
The fact that it's two-dimensional, it only means that you still have a shock plane, which is not a plane; it's a line in 2D. So you have maybe I should. So one option is like that. This is the shock propagation direction, and one option is that you have a particle distribution elongated along the shock propagation direction. Symmetric, more or less symmetric, something like that. Oh no, the first option is not this. This is the third option. The first option is actually that it's beamed forward. So this is the center of the distribution, and it's elongated along the shock normal and beamed forward. The second option is like that. It's this is the center, it's elongated there and beamed backward. And the last option is that it's flattened and not elongated. This is the fourth option, is that it's like that. And this is the shock propagation direction in all the situations. So, who votes for the first? Oh, come on. So you have your vote, but no one is going to vote for first. No? Really, no one? Okay, good. We have one vote. That's it? Okay. Second option is that particles are beamed backward. So in the shock frame, they are moving in the opposite way. Who votes for that? One? Oh, many. 1, 2, 3, 4, 5, 6, 7, 8. Right? 9. Good. 9. Can you see it?
Yep.
Okay, the third option, that there is no preferred direction, but it's elongated along the shock propagation direction. Who votes for that? 1. That's it? Also 1. Okay, then it kind of having trouble. Okay, and for the last option, that it's flattened and not elongated, who votes for that? 1, 2, 3, 4, 5, 6. Okay, 6. So here is the winner. And you know where is the right answer? Yes, you should know. This is the story that I actually told in the Baksan school, where, which was beautifully run by the same organizers. The story is like that. I'm always trying to get any opportunity to ask students use their intuition and tell me answer in a problem where it is not at all obvious, just using their intuition. And I was trying to see if the majority is ever right. So far, the majority was always wrong. Now, it's not an exclusion, the majority is wrong. But, you know, the second place is the right one. Now I know the answer. And I will show you this answer. So you see the distribution of particles, and most of the particles move at 90 degrees to the shock propagation direction. Why? It's understandable. Because if you cross the shock, given the fact that I showed you the geometry of the magnetic field, if you cross the shock in the shock direction, then the scattering depth is not that large. So which particle stays into the acceleration process? Which particle stays? The ones that go almost along the shock direction. Then they can scatter many times. Each time they will gain much smaller energy, but this is compensated by the fact that they stay longer. And if you plot the distribution of the time that the particles spend in the shock, close to the shock, then you just exactly see that. So this is basically the final message of my talk, that there is a lot new in the physics of acceleration and the shocks, which is yet to be explored, and it's not just new, sometimes it strikes your intuition to the extent that you won't believe your eyes until you repeat it many, many times and see that, yes, this is it. And then after that, as in the famous joke, you see it once again and you say, oh, it's obvious. Of course it should be like that. But you cannot do that before. Okay, thank you.
This is very stupid. Sorry. Related to the, I thought, can't you just use, for example, you're writing on a very relativistic frame and somehow the lens contraction makes you, at least I was thinking just in the stupid Feynman-Parton distribution picture, that the lens contraction writing.
It's in the shock frame, so
it is.
It is. If you, it's not a contraction in the momentum space. It's you stretch the particle distribution, not contract. The momenta they are not contracted; they are stretched, right? because the phase volume is conserved in the Lorentz transformation. You contract the space and you extend the momentum.
Yes.
So yes, in the lab frame, this distribution is very elongated along the shock propagation direction.
Right.
So it's not because of that. If you are on the shock frame, it's the reason is different. The reason is scattering properties of the particles.
Okay.
They are much easier to scatter if they move, just by chance, if they move along the shock plane, they scatter many times. If they move across the shock plane, they quickly lose the region where the magnetic field is high enough to scatter the particles. They go into the regions where we have the sparse magnetic islands, and they just go away.
Okay.
That's
So
it.
really
But this is, once again, just to make it clear, this was the simulation of diffusive shock acceleration. And I should tell you that I don't know how to simulate, in particle and cell, how to simulate the converter acceleration. Not in the way that I don't know how to do it, but if we try to do it, we see many unphysical problems that we have still to solve, and we are trying to do this. Still, so far, no success. Okay.
So, other questions?
Well, the question is related to the observational possibility to distinguish between the converter and the standard acceleration model. So it seems that a converter model produces plenty of neutrinos, and there also might be
Yes.
interaction with the cosmological microwave background, and could it produce observational signals on the Baikal telescope and probably on the cosmological microwave background even? So can we correlate the hotspots and the gamma ray bursts?
Yes, thank you for the question. It's really a good question. Indeed, if you do the converter acceleration of protons, you produce pions. This is inevitable. This is the very essence of the mechanism, so you should produce neutrinos. This is not, in any case, this is not a distinctive feature of this mechanism. This mechanism must produce neutrinos, and the other mechanisms may produce neutrinos, but the conditions are such that it's really hard to distinguish between a situation when you just say that somehow I produced very energetic protons. Let's see if we have neutrinos. And yes, we have interaction with photons and we do produce neutrinos. So it's not that easy to distinguish on that. Though you are absolutely right, this is a distinctive feature of this mechanism. You must produce neutrinos. Regarding the question whether we will see these neutrinos or not,
but their spectra should be very correlated to the spectra of energetic particles. So this can be a
yes, but we don't know what are the spectra of energetic particles.
Yeah.
no, once
That's
you
the point.
predict a spectrum of energetic particles, at the same time you predict neutrino spectrum, and this can be different from the conventional mechanism.
Maybe it goes the other way around. If you know the spectrum of neutrinos which are produced, you can think of the spectrum of particles. Why? Because this mechanism, as any other mechanism, actually depends on the details, and you have huge jumps in the energy each time, and each time you more efficiently interact with a different part of the photon spectrum. So you have to know the photon spectrum to a good precision, which is not at all easy. Even if you measure the spectrum at Earth, you have to know the normalization, which is not at all that easy. So in principle, yes, but in practice, I think that it should be done the other way around. You measure the neutrinos and then you guess on the spectrum of the particles. And regarding the sensitivity, if our Chinese colleagues will push all the Chinese industry to produce many photomultipliers, then maybe we can produce big enough detector that will see any gamma ray burst. But now we have to rely on chances. I don't know. If you have a chance, maybe.
Thank you for your questions. I have one question. For lecture, excuse me. Thank you for your lecture. What difference between gamma photon soft and gamma photon hard.
Oh, you mean in the slides? Okay.
28 slides.
No. This is the inverse Compton interaction, and if you have inverse Compton interaction, you have high energy electron hitting on the low energy photons. Low energy photons are usually in astrophysics they are called soft photons. Maybe I should have to explain that.
Different for energy.
Yes, the energy is very different. This photon essentially has the energy similar of the initial electron, basically 1/2 of this energy, and this photon can be much less energetic. In this cycle, you can definitely say that this photon should have energy very well below mc squared.
Okay, thank you.
Very much for the lecture. I have some questions, and first is when we're talking about this problem, can we just think that if we stay in the reference frame of the shock and these magnetic particles, they're just moving to us and we should change our direction so that it's not our direction?
I'm not sure that I got your question.
So this was while this test, like on the blackboard,
Which one?
on the whiteboard.
This?
So when we are staying in the shock wave, we just see the magnetic field particles moving through us, right? And then we should interact with them and just change our direction.
If we are in the shock frame, then, well, the magnetic field is kind of, it's not exactly like that, but it's kind of frozen into the plasma. So the magnetic field lines, if we see from the shock frame, the magnetic field lines in the upstream, yes, they are approaching us, but once you cross the shock, the magnetic field line starts to recede from us. Was that the question? Or?
Yeah, and then we just cannot stay in the same direction. We should go to the field.
You mean if you want to choose intuitively between this one, and the one which has no preferred direction, then why we should have a preferred direction?
No, I mean we shouldn't stay on the same axis, so we should be perpendicular because of magnetic field. We should change direction somehow.
We shouldn't stay on the same axis. When I have drawn this distribution, that only means that you have fewer particles moving in the transverse direction than in the forward or backward direction. It's only a question of numbers. It doesn't mean that there are no particles that are moving in the transverse direction. But the result, as you know, the result is this one. There are more particles moving in the transverse direction, so they are more likely to move in the transverse direction after the scattering.
Then the second question is about magnetic field picture. So why is it particular?
You cannot judge this from the geometry of the magnetic field alone, because yes, if you consider every single interaction, it's kind of isotropic. It has no preferred direction. You're absolutely right. But if you think of many interactions, then a particle that moves along the shock sees closer to the shock, these islands are more magnetized and they have a larger size. So close to the shock, the scattering probability for a particle is larger. And scattering probability doesn't mean that you just strike the wall and go backwards. Usually it's a deflection by some angle which is not very large. This is more, in terms of probability, this is more probable process than scattering just like from the wall.
Yes, but the question was just why the magnetic field picture looks like this. Why is it not homogeneous, but just this islands, bubbles?
You know, I have to repeat it once again. There are excellent questions when you are prepared to answer. You know the answer and you are prepared to answer. There are very good questions when you know the answer, but you don't have a slide ready to answer. And this one is a good question because I don't know the answer.
But was like.
I can tell you some hints from intuition, so to say. It's not at all a strict proof of the situation, but intuitively you may think of the situation like that. You have some instability at the shock, and closer to the shock, this instability is the strongest because this instability is caused by anisotropy in the particle distribution. At the shock, this anisotropy is the largest. So this instability is the highest, and you start to produce the magnetic field from this instability. It goes higher, higher, higher until you reach the shock. And afterwards, the magnetic field cannot be fed from this instability because the instability becomes weaker. What should happen to the magnetic field? It just starts to decay. I told you that it's kind of frozen, and so it's not exactly frozen. It decays. It slowly decays, and that's why far in the downstream you see the magnetic field, which is smaller. The islands are smaller in size. The islands are occupying less space, and the overall average magnetization becomes smaller, and the probability of scattering becomes smaller. So it's the scattering is confined to the shock, where the highest magnetic field and the highest rate of producing this magnetic field. But this is just very, qualitative picture, and quantitatively it's very hard to describe.
And the very last question, sorry. So when we're talking about protons and it doesn't radiate, so we cannot test protons in this sense. Can we do it on some other heavier particles like muons, maybe?
Muons? Well, in principle, you can accelerate muons. The question is the acceleration time. The acceleration time, where is the acceleration time? The acceleration time is in the B. If you remember from the first lecture, it's the acceleration efficiency times charge times C times B. If B is high enough, then you can accelerate a muon before it decays. If B is not high enough, then you cannot. I did some estimates for the presumed internal shocks in gamma ray burst outflows where the density is high and the magnetic field could be as high as 10 to 6, 10 to maybe even 10 to 8 Gauss in some extreme cases. Even that is not enough. Maybe under some even more extreme conditions you can accelerate muons, but normally you don't. Not because you cannot accelerate them, but just because it takes too long for them and they just decay.
So, if there are any questions that are
Yeah, I want to ask you a question which I probably already asked you in the past.
No problem.
Yes. No.
Then you can check whether my answer changed or not.
Yes, maybe you evolved during these few months. So the question is the following. In principle, all the physics which we are dealing with is known. I mean, you are not inventing no standard model, anything like that.
Yes, if you go for new physics, then you are done. In the sense, they will kill you immediately when you are starting to introduce.
So we are basically talking about different approaches how to solve the problem. So either you're considering some analytical considerations, some numerical stuff, and so on. So and in this regard, I'm wondering, so are we really close to create a kind of really fundamental set of equations for the plasma, magnetoplasma, all the particles, and solve kind of Boltzmann equation, which should be the finally, to me, just a solution numerically. Even, okay, you can be still based on some intuition, analytical assumptions and things like that to drive the solution, but in the end, this should be just a pure numerical solution to the problem. So I think we should not really guess what is the mechanism whatsoever. So this is just, an explosion of something like a supernova or gamma ray burst or whatever. So all the matter so this should be just coming out from the solution of the equation. And I'm just okay with a numerical, why not? I mean, if it can be done carefully.
Well, you know that, of course, but maybe students need that answer. If you have just numerical results, Andrei Gruzinov once told us that if we calculate everything on the computer, then we know everything. Then he corrected himself. Well, the computer will know everything. We still don't know. If we have just numerical results, we still don't know the situation in the sense that we produce numerical results for a certain set of parameters. Now imagine that something comes at hand which has different parameters. What should we do?
Just repeat.
It's easy to say, but these simulations, very simplistic simulations, take months.
No, I mean, in the high energy community, people are using software like Jump4. So this is just like a Bible with all known physics. So, and this is kind of standard tool. Certainly, if you change parameters, you will get another answer. But if you change parameters, you will get in conflict with other observables. So in principle, this is just a collection of known physics, and then you're just doing by Monte Carlo simulation, you're looking for the solution.
This probably could work if we can do simulations at the blink of an eye. Then yes, but unfortunately we cannot. All astrophysical simulations are very heavy, and even these simulations that are very heavy, almost at the limit of our computational capabilities, they are very, very much simplified. To the extent that I wouldn't believe them in some cases. Not just to believe that they are exactly correct, but sometimes I wouldn't believe them even qualitatively.
Okay.
They are too much simplified.
You're consistent with your earlier answer.
So we have, I think, last question. So because there are only 10 minutes for break.
Okay. So very naive question. Maybe this is maybe related to the first question. Now, Larso observed so many PeV gamma sources, and I thought the conventional wisdom is an electronic model. But I don't know whether in the converter model it works, but looks the conventional wisdom doesn't work. So it's a hadronic. Maybe you have to use the converter model to predict those. The question is then the fact that nobody has seen any coincidental neutrino signal. Is this consistent at least with all consistent with the fact you don't see neutrino, but you see all these gamma rays under the hadronic converter model? And conversely, the NGC 1068 saw many neutrino, but nothing related to gamma rays. There has to be, yeah. I mean, I asked this question many times, never get a solid answer. Is there any picture that can make everything self-consistent?
Yes, the second situation is relatively easy. Easy in the joke sense. I can always say that okay, you have so many gamma rays, soft gamma rays that are producing pions that then later give you neutrinos. Neutrinos freely escape, but there are so many soft gamma rays that the Compton high energy photons are just absorbed. So to have a neutrino source which is not absorbed in gamma rays at reasonable luminosity is just fine. Yes, sometimes you have to push the parameters to the limits, but it's not tension in the fundamental sense.
Okay.
On the other hand, if you want to produce PeV photons and not produce neutrinos at all, that could be a trouble, because any hadronic model, no matter whether it's a converter acceleration or not, any hadronic model would produce neutrinos. So then the question is, can you accelerate electrons in one or another way to go all the way to the PeV? And then I would say that that converter is kind of preferable, because there are some cheats in the converter acceleration, because you not just gain energy slowly, then you have a limit. This limit for the maximum energy was introduced because you can balance the continuous losses with continuous energy gain. In the converter acceleration, it's not really continuous. You go in big leaps. So in principle, you can go beyond that. But it's not that easy, even though. But yes, it's a very good question whether we can explain PeV photons with the converter. Very hard.
Thanks.
So let's thank the lecturer again.